All right, we'll go ahead and get started. Appreciate everyone joining us today for this webinar on hydraulic structures controls in EFDC. My name is Paul Craig, the principal scientist developer for the EFDC Explorer modeling system. And today we're going to be talking specifically about some of the new features and capabilities that we have added to the EFDC Explorer modeling system for hydraulic structures, principally for dynamic control of the hydraulic structures during the simulation. Historically, EFDC has had hydraulic structure capabilities to input rating curves and such into EFDC, but they couldn't change with time. So with this new ability that we've added, you can now control it based on water levels and other processes that are going on inside of the model domain. So to get started here, we're going to be covering the flow control structure, talking about gate controls and withdrawal return controls, then describe a hands-on session for building and looking at these models in a simple test case, and we'll have a period of question and answers. So as I mentioned, originally EFDC had the ability for putting in rating curves into EFDCs for the simulations that could be based upon a upstream depth, a elevation difference with accelerations, and upstream downstream elevation. So you just had your typical rating curve of some head value based on these water levels, and then a associated discharge with that particular water level. Subsequently to those, actually in 8.4, DSI added this capability for a typical rating curve for the entire channel, and allowed for splitting individual cells up for the discharge. As if you have just a rating curve for the entire river, you can enter that and then use that, which is very similar to these other methodologies. But what we've done in 7.2 is we added some capability for what we call low chord structures, which essentially handle bridge obstructions where there's a free flow of water below the bridge, but once the bridge or the water levels reach the low chord of the bottom deck of a bridge structure, it begins to act more like an orifice, so we can adjust the hydraulics accordingly. And then in 8.0, we added hydraulic structures as equations. So you had sluice gates, orifices, weirs, etc. A very general capability there. Now what well, let's just look here at the hydraulic structure kind of logic flow diagram for sluice gates, which is what we're going to be talking mostly on today, is just focusing on the sluice gates for a series of uncontrolled and then controlled approach. But this is the logic process by which EFDC Plus will go through the process of deciding how to calculate the flows given a particular water level and the gate openings conditions. So you've got everything from supercritical flow and subcritical flows and submerged flows, and EFDC is handling these flow conditions and deciding appropriately how to conduct the actual hydraulic calculations. So now what have done with 8.4 is we've added this ability to control these structures with either a time series where at a particular time the gate is operating in a particular position, opening or sill height, etc. Those things can change with time, as well as changing the behavior of the condition of the gate based on water levels, either at a single reference point or by the elevation difference between two reference locations. So either one of these can be used. And just as an example, we're looking here at typical approaches where you have a gate where the gate height is changing with time, and that would be, as an example, a tainter gate where water levels are varying and the gate can open and close either based on a time series or based on the actual water levels. Another type of temporally varying hydraulic structure is when the widths of the gate are changing, as an example of, say, navigation locks. Another example would be where the bottom elevation or the sill elevation changes with time. With these typical kinds of gates, you've got an inflatable gate, or you've got some kind of movable gate, as you can see here. And then another feature that has been added is the ability to control the withdrawal return process dynamically within EFDC based on water surface elevations, either, again, whether or not you're looking at a single elevation location or some kind of elevation difference between two separate reference elevations. So in this case, essentially, it acts like a time variable pump that responds to a particular elevation in the system. So typical examples, of course, are for withdrawal return systems or power plants, which could be either temporally controlled or controlled by some available water conditions in the intake or the receiving water body. So with that kind of brief overview of the capabilities, let's look at this simple example that we're going to discuss today. And it's a very simple rectangular channel where we have like a river flow coming in at the upstream end, flowing down through the system. Then we have essentially like there's a dam or some flow obstruction here in the river. And then downstream of this flow obstruction, there is a tidally influenced downstream region that is changing with this semi-diurnal tide here with an amplitude of 1 meter. That's affecting the water surface downstream. So you have this upstream flow and then this tidally influenced downstream. And then at this flow barrier here, we have constructed this sluice gate that has a width of 100 meters, which is essentially, likely to be, a series of multiple sluice gates operating in unison, so we can just address it from a hydraulic perspective in this model as a single gate with 100-meter width. And then the height is 3 meters. And the Z, this is the bottom sill elevation, is at -1 meter. So this is the simple layout of this example. So we'll build it where we will have, this is the grid, and this is an example of screen capture from EFDC Explorer during the construction of a model. So you have the model domain, the model grid. You have these boundary conditions as indicated here by these check boxes. For the upstream river, you have the tidal boundary on the east edge of the model domain, as indicated here by these E's in the model grid cells. This gray bar here is the mask where it prevents any flow from this cell to this cell or any of these cells along this flow path here. So the only way for water to move from one side to the other is via this sluice gate here. So that's the basic configuration. As I mentioned before, we're looking here at a semi-diurnal tide, the M2 tide with an amplitude of 1 meter, and fresh water coming in, 0 parts per thousand. We have some dye assigned to it, so we can kind of look at the flow pattern of the fresh water and as it moves around in the system. And then the downstream end, we have a constant salinity of 30 parts per thousand. So to define the sluice gate, this again is all within the EEMS system. You would set up the boundary condition and then tell it you want to build this a sluice gate. So what type of, give it an equation ID and tell it what type of hydraulic structure it is. You can optionally decide whether you want to allow reverse flows or not. In this case, we do. So flow can move both upstream and downstream. And then you define all your parameters here, sill elevation, opening heights, widths, etc. in your hydraulic coefficients, as shown here. And once you've kind of configured your boundary condition, we can then apply it. Let me go back here. So this, if you just applied this approach here, all we would have would be a uncontrolled structure. So the gate is constant at always at a height of 3 meters and always a width of 100 meters. And the only thing that's varying is the water level upstream and downstream affecting the flow through this gate. So that's an uncontrolled sluice gate structure. The controlled sluice gate would then raise and lower this gate structure here as shown in this little diagram based on whatever however we have configured EFDC, either just a time-based value or actually a water level values. So we're not going to step through everything here, but we're going to jump over here pretty soon to the actual EFDC Explorer interface and look at some of these, but we'll provide these runs on our website, so you can download these and play with these examples if you have a demonstration version or a full version of EEMS. But run 1 is the uncontrolled condition. Run 02 is using the same sluice gate settings, but we're starting to apply various control rules here. Then this particular example here is just actually just straight up using, making the assumption that we know how the gate should be operated on a time series basis. So at a particular time of day, the gate raises and lowers according to the timing that you've specified in a time series. And then finally, run 04 here is the example using pumps instead of a sluice gate. So just looking at the uncontrolled case here, so you'd start up the model or EFDC Explorer, and by clicking on this button here, you can create a new model. Then in this screen here, it shows what the settings are in order to build the grid, as seen in the examples before. But we're looking at a delta Y of 100 meters and a delta X of 200 meters, and this is the number of cells in the X direction, number of cells in the Y direction. And so by making these settings and then applying some kind of initial bathymetry here, you can set up this simple uniform sloping bottom test case. So that builds the grid. Once you have the grid, you can display it here in the EE interface. And then we'll go through the process of setting the boundary conditions here. We have to assign a flow boundary and a dye boundary and salinity and water levels, and these things all go very quickly with EFDC Explorer. And these just give you an example here of the time series for the upstream flow. It's just a constant flow of 200 cubic meters per second coming in over a 30-day period. And then the salt time series for that we're going to use for our freshwater or the riverine condition of 0. And then we have a dye series for the upstream river flow, where we have a dye condition of 10 milligrams per liter constant for the entire domain. Now for the downstream boundary, for the downstream boundary here, we can apply for the tidal series, we can either apply a actual time series of time and water level, which is based on the M2 tide, or we can actually apply harmonics, and we'll look at that a little bit later. So that's the water levels that we're applying to the downstream boundary. Here's the salt series. As you can see, it's a constant for 30 parts per thousand for a 30-day period. And then the dye over on this side is 0 concentration. So this is what the model looks like for the bottom elevation, sloping from -1 to -1.6 essentially down our theoretical river. And here we're just looking at bottom elevation. This is the 2D plan view viewer that is one of our primary viewing and editing tools within EEMS. So now we have this river and all the cells are connected, so we need to build this dam so that we can prevent flow from moving from through this structure that we are assuming is in the middle of this river. So to do that, you could disable a row of cells if you wanted to, but these are 200-meter wide or long cells, and it may not be physically realistic to do it. So we're making the assumption here that there's a thin dam, barrage, something that prevents flow from moving from the upstream end here to the downstream end. So these are constructed using what we call masks in EFDC, and we just apply those to this face between these two cells, and that prevents any flow between these two cells. And they're defined here with, you can just click on the cell and turn on a mask on either the west face or south face, but what you end up with is these, a series of masks. And you can click on each cell and do it manually, or you can use a polygon and select all the cells that you want at one time. You'll notice here when you go to edit those, you see the number of cells that were selected were 10. You just check this box one time, and then all the cells are set at once. So that's just a quick way to be able to set these. So the rest of the boundary conditions here, we have the upstream flow boundary, the constant flow. These are timing frames that EE can display to help provide a temporal reference to when you're looking at 2D images of the model domain. Here we show where we've set up the gate structure here. We're not showing the mask, they're not turned on right now, but the mask would be located here. So the upstream cell, this particular I and J, here's the information, and then when you click on the cell, it gives, whoops, when you click on the cell, it gives you the information about the, if it's a boundary condition, gives you the ID here, and then provides some information on the current boundary condition for that structure. So here's the upstream cell, and this is the downstream cell for the gate. So to create that, you would click on the cell, but this is assuming this is before we actually had the boundary condition assigned. So this is how you do it. So you would right mouse click on the cell and tell it new. Then you would select what type of boundary condition you have after you've given it some name that makes sense for you as the user and model developer to give it a physical or a name that's descriptive of what it is. Tell it what type of structure it is. Then on the EE would open the hydraulic boundary structure form, and in this form, the user would tell the EE what kind of equation it wants to use, and the downstream cell would have to be specified. So the upstream cell and the downstream cell are right next to one another, but you just type in these, the downstream cell, either L or the I or the J, either one. This pair equals this, and the L equals these, the I and the J pairing. So once this is set, which is, as I said, simple number, then you come over here and you define the equation. And again, we give it the actual equation name is gate, and downstream cell, yep. We jump here to the sluice gate. So now we're defining the actual sluice gate equation here. And so with this, we have to identify all the parameters. So this, you enter the sill elevation, the height of the gate, the width of the gate, and then the hydraulic parameters that apply to that particular gate. And as I mentioned before, you make sure we check allow reverse flows. So with that set, this boundary condition is now defined, but it's defined as uncontrolled. Next thing we do is just turn on the activate salinity and dye constituents so that we can now define these parameters for the simulation. And the other, the rest of the parameters that we have to set up for the initial model development are the turbulence and wetting and drying, if we needed to. In this case, not really needed for the particular application, and some specifics on how you want the hydrodynamics to be solved. Most of these things all have defaults for EFDC that work quite well under a broad range of conditions and make it relatively straightforward for the user to assign the conditions. But this set here for the setup of the timing and for linkage, this is very model specific. And here the user defines the start time in Julian days from some base date. In this case, it was January 1st, 2010. And then the number of reference periods and then the duration of each reference period. So this would be essentially a 1-day reference period. So this simulation will run for 3 days. And then the time step. This is the hydrodynamic time step that will be used by EFDC. And EE has a tool here where you can initialize and make a first pretty good guess of what the initial time step should be. And then from that, it will assist. You can, of course, maybe during model testing, raise or lower it according to what some more of the details of the actual model configuration when you're actually running some tests, but this gets you pretty close to what it needs to be. When you're doing 2 time level solution, which won't get into the difference between 2 and 3 time level solutions right now, you can also use dynamic time stepping, but when this is set to 0, dynamic time stepping is not used. So in this case, we're not using it. Then another important parameter here to set before you run the model is how frequent do you want to link EFDC plus output to the post-processor of EFDC Explorer. So the model is running on a particular time step and doing all the computations, but you still have to output that information at a particular set of user-defined time steps. And this is where you set that. So here we're setting it to 60 minutes. And so there will be files that will be generated by EE every 60 minutes of simulation time, and which we will be able to post-process and look at after the model finishes. So we'll set up the initial conditions according to these parameters. So essentially everything initially is set to 0 with a bottom roughness factor, Z0 of 1 centimeter. So once we've got this model saved up, or built up as we have just done, we can save this model out, and we could save it and give it a name. And in our particular case, we're calling this run R0 as an example. Once the model has been saved, you can then run the model. This is your typical run form. Basic information here with EFDC plus. With 8.4, we now always release the multi-threaded version of EFDC. So this is telling the user here in this example that there are 4 hyperthreads available. We have a whole separate presentation on talking about how to use multi-threaded applications and get the best throughput for your particular example. But in this case, I'll just tell you that with the 4 threads indicates that there's 2 as actual physical cores. So this is your typical i5, Intel i5 system. And to get your maximum throughput, you just enter half the value of your threads. So we're going to use 2 physical cores. So both the cores are going to be fully utilized by EFDC in this example here. And then this is a runtime status, just something that displays as the model is running and gives you the information about what will be displayed and at what cell and what interval. And here we're telling it we're going to use post-processing, but in the prior slide, you saw that 60-second or 60-minute frequency. At anything that you enter under this form before you press run overwrites what may have been in the prior form. So this is just kind of your last chance to make any final adjustments to the inputs before you actually run the model. So when you click on Run EFDC, this is a typical example of what is displayed. You've got the model running. It's this typical, it's a command window or a DOS window where you've got a timestamp. This is the time step reported, water surface elevation in centimeters. And all this information that's displayed on each one of these lines is at that one cell that we mentioned or that we provided here on the input, the run form. So this we'll run through in a very quick order in this particular example. And this is the Salinity time series extracted for that 3-day period from the model at this particular cell, just as an example of the type of information that will that we can generate with the model. And once we actually open up the tool, we can look at it in a lot more detail. So to apply a rule-based sluice gate control, we'll just use this original model, what we call the uncontrolled model, and then we will build in the properties necessary to adjust the timing of the opening conditions for that sluice gate. So to do that, originally with the R01, we had it set up here to uncontrolled. So now we're going to change it down here under the time control to control by elevation difference. And once that's done, this frame here will become enabled, and we can click on this edit button and go to setting up the actual rules for that sluice gate. So to do that, we've got this form here where we can, depending upon what you're actually trying to do and the complexity of the system that's controlling that sluice gate, you can define numerous rules, and then this is just the current rule that we're working on down here. And then each rule can have a whole series of triggers that enable a certain operation to initiate, either the gate's opening or the gate's closing, and they can open or close to a specific height in this case, because in this particular rule, we're changing the opening height. We could also change the opening width or the opening sill level. But in this case, opening height selected, so we have the height column here. And then the state is an indicator that whether or not the gate is opening or closing. So, excuse me. In this case, we've got a condition when the water level difference reaches 0.5, the gate will begin to open at up to a maximum of 3 meters height at a rate of 1 meter per minute. So that's a fairly fast gate opening, but you don't want this, rate to be instantaneous because basically it can shock the system, and plus that's not the way these gates can physically actually operate that fast. So we just control the rate of the adjustment. And then finally, once the water levels go through the cycle, and then the difference between the upstream downstream is 0.2 meters, the gate would begin to close, and it'll close all the way to 0 gate height. And again, the rate of that movement is 1 meter per minute. Once we've done that, the last thing we need to do is just set the initial conditions for the gate operation. And so we can set it here as to what the gate is currently opening or closing, and what the open height, width, and sill level changes are. So right now we'll just leave it to the gate is closed and in the initial condition. So once that's done, we've defined all this information before. So we had previously defined, the cells and the actual equation. Now we've changed this control based on elevation difference, and now we've just applied these control rules to that set of conditions. So, and this is the operation looking at time series of the two different test cases. One, the green line was a salinity at the cell 21.7 with the uncontrolled case. So this is upstream of the hydraulic structure. So originally, salinity was making it from the ocean, if you will, the higher salinity region, upstream through the hydraulic structure, and essentially getting salinity in the freshwater river. So in the rule-based case that we just created, that is this red line, and essentially it's just, you know, being drawn essentially as 0. And so there's, we have prevented with this rule-based approach the salinity intrusion upstream by changing gate operations with time that are controlled by the tide levels. So this is a rule-based controlled example. So we can do the same thing with time series based control. And this makes the assumption in this example that we just, you know, at some regular operation of the gate that the gate operators already, you know, have predefined. So here you're just defining the gate operations on a known time series. I'll just assume that, you know, all these things are, you know, we've already discussed how you get to this point, but once you've come here and selected control by using a time series here under time control, then you have this time series option here where you specify the time, the height, the width, sill elevation, units and status and flow if you've got different, you know, pumping operations. So you set this up. You tell it which of these columns you want to apply. In this case, we're applying the opening height here. So this time series that will apply to the model will be the opening height. And then as you can see in this example here, that the gate operations are changing from, you know, 3 meters high to closed to 3 meters high to closed again with this particular number of Julian days from time 0. So with that all set up, we run the model again, and we can look at the output here in a minute on the real-time based results. So finally, we can set up this pumping system, and it's very similar to the hydraulic structure, but here we're actually using a defined withdrawal return. So we are withdrawing a flow from this cell and discharging it back into this cell with a defined flow rate. So going through the process, we would set up the withdrawal return boundary condition across that flow barrier there. And here we're setting it all up just as we have done with the hydraulic structure. So we've got our upstream cell, our downstream cell for the return. Then we set up the control rules for the hydraulic structure. Just once you've turned that on, you can set the state again based on these control values. Here again, we're using with a elevation difference, and you know the pumps are turned on or off, and then what's the actual flow rate for these conditions for this particular rule. For in this case, we just have 2 triggers for this specific rule. So with that set, everything is set for the condition to be able to run the model. The initial flow discharge is set to 0 cubic meters per second. So these are now all defined. You got rule-based control for withdrawal return based on water level difference. We've got the control rules set, and everything is ready to go. This is what it looks like in the plan view. So this is the withdrawal cell, and this is the return cell. We run the model, and then we can look at the output. So with that kind of ends the presentation portion of the withdrawal return section, and then also the hydraulic structure section using time variable controls. Are there any questions at this point before we move on to some of the hands-on with the actual tools? Okay, if I don't have any questions at this time, I'll move on to actually looking at EFDC Explorer and what we can actually do with the tool. So here is the EFDC Explorer main form for the pre and post processing of the EFDC Plus code. And this top toolbar has some of the main functions, but these three buttons here, this is the 2D slice, or I mean 2D plan view. This is a 2D vertical slice through the model domain, and a 3D perspective of the model. So just looking at here at 2D plan view, so you can see here the model grid, the boundary conditions. We can scroll through. These are the different options that we can look at. Here's the bottom elevation, the water level depths, the water level initial conditions for elevation. Then there's various fixed parameters that you can view based on what you're simulating. The information that's displayed in this list here, and then what is displayed down below in this panel, is dependent upon what you're actually simulating. The more processes that you actually turn on and simulate in EFDC Plus using EFDC Explorer, more options will become available up here, and you can view essentially everything that you're simulating with EFDC Explorer. This top toolbar here are predominantly functions that operate on whatever is displayed down here. So this panel on the right sets what you are viewing. This panel at the top provide actions on the current view. So let's look here at water layer by depth. And so here, as we mentioned initially, everything is zero concentration for salinity. And the dye also zero. Let's look at the, so here's the masks. Let's go to boundary conditions. And let's edit this boundary condition here. To do that, I right mouse click on the boundary cell. So in order to actually edit any of these 2D plan view settings, you have to enable edit first. So once that's turned on, then you have editing functions enabled in EE. For instance, I can come over here to the upstream boundary, right mouse click on the boundary, and I can either view the group, which is the total flow through all the cells, and that was 200 cubic meters per second, or I can view each cell individually, and so this is the total flow through that particular cell, or I can edit that boundary group just by clicking on it here and look at the number of cells and all the linkages between flow and that cell, and then the concentrations in that cell. So these are all available here on this form. And then likewise on the downstream end, we can edit the water level specifications here, and this is the time series for pressure, and I can edit that. Take a look at at what we've assigned. I can generate plots of the data. So that's the time series that we're using for the downstream boundary. And then finally here, just looking actually at the hydraulic structure, let's edit that. And so as we were mentioning, so this is an equation based on a sluice gate, but these are all the options that are available to us. The whole channel rating, all these are rating curves. We have the low chord options here. And then we have the equations for a culvert, sluice gate, weir, and orifice. So again, we were doing the sluice gate. And then here's our timing control. Initially, it's just uncontrolled. So we set all that up. And then down here, for defining the equation for the sluice gate, you do that down here. And you can have multiple equations for multiple sluice gates, in your model domain. In this case, it's simple, so we're just having one sluice gate. If you had one sluice gate, you can split the flow between multiple cells or increase the flow using this distribution factor. But right now, everything is just one boundary condition, one cell, and one equation. So editing this is the hydraulic structure, the sluice gate here. So we have that specified, again, allowing reverse flows. And we've already talked about all this, but this is how you set it. That's all done. So once you've configured all this, and I can right mouse click on, the boundary group and see the time series for that group, we can run the model. So with that, I will save this model and just make the assumption that, I hadn't saved it before. So now it's saved. The last thing I need to do is, this is the first time you've ever done set up the model. You want to make sure that you're pointing to the executable that you want to use for this application. So here we're using EFDC plus and that particular release date, July 7th. So with that set, I then just run the model here, and this is our form. This particular computer's got 6 physical cores, so I have access to 12 threads. I can run it with 6 threads, or I can run it with 4 or 2 or 1 or whatever I want. So we'll just leave it at, let's just change it to 6 for now. Output every 15 minutes. And everything else looks fine. It's going to run very fast across this screen, so I'll slow it down a little bit. Run EFDC. So here's the model running. It's going to run for 3 days. So we're down already day 2 days, and now 3 days. So the model has now finished running. We have output every 15 minutes now that we can look at. So I can come in here to the 2D plan view, go to water by layer, and as an example, look at the time series of salinity. So just look at the masks. There's the mask. So if I want to look at the salinity, say just what's the salinity just upstream of the mask and what's the salinity just downstream of the mask, I just click on the 2 cells that I want, and they're displayed in this list here. When I get the cells, all the cells I want, I can select the show button here. I can save out that list, and I can load up another list. So these are just some of the options available here, but let's just look at show. So we have 3-day simulation. So there is the time series of the salinity at the 2 cells, essentially right along that mask. And as you can see, the salinity upstream and salinity downstream are almost identical, even though we're talking about upstream and downstream of the mask. So if you're trying to, have a hydraulic structure that's trying to prevent salinity from moving upstream, then obviously that's a problem. So you need to adjust your structure openings based on the tide levels to affect the or to prevent that salinity from migrating upstream when you have higher tide levels. So if you look at it in plan view and we generate an animation here, let me make the form a little bit bigger. Come on. There we go. Nope. My mouse is, there we go. So I can look at salinity at different times. If I turn on my what I want to do there. Oh, timing frames, that's what I was going to do. Come over here, turn on my timing frames. I can see what the tide is. So if I look at the downstream condition, and then I look at what the river flow is upstream for 3 days, and then you can see what the actual tide levels are doing at these different times. So if I want to see what it looks like at high tide, I can just right mouse click here and go to time, and you can see here that the salinity is coming in at 30 parts per thousand, but we have 200 cubic meters per second moving downstream. But at high tide, the salinity is still being able to penetrate the system and move upstream into the quote unquote freshwater system upstream of the mask. So I go to the low tide condition, and you can see basically it has pushed all the salinity out through the domain because there's such strong freshwater flow, but we still have a little recirculation on the edges and a little bit of salinity still hanging around in the system, but albeit a very small number. So that's the results. So now, finally, what we'll have time for now is just looking at the controlled gate. So let's look at this condition here. I am going to run this model while we're talking about the other setup. So with that, those changes, the model is running, but while it's running, let's just look at the configuration, domain, boundary conditions, click on the edit review, and then look at the gate here. So in this particular case, now we have the control rules set up. And so we now have these control rules configured. So now let's see what the salinity does with this setting now based on those control rules. So with that, the model has finished running, as you can see over here. So now we're going to be looking here again at this region here, and I want to know what the salinity is upstream and downstream of the small dam that exists in this theoretical river. Again, just bring up the time series, select the two cells that I'm interested in extracting, looking at salinity, and show those data. And now, bottom elevation. First I have to go to salinity. As I mentioned, these tools up here operate on whatever's displayed. So we got to go here to the salinity water by layer and then pick the salinity as the option that we want to look at. And then when I go to time series, they're still defined, as you can see here. So I can just click show. And now we have two conditions. This is the upstream cell, so let's make that one blue. Let's make the downstream cell red. Both cells will make them a little thicker line so we can see them better. And there we go. So now we have the upstream, the condition that we wanted is fresh water stays fresh, and the downstream is moving with the tide and the freshwater forcing that's pushing through the system. And so you have saltwater, freshwater, saltwater, freshwater conditions. So with this, we're essentially out of time right now for this webinar. If you have any questions at this point, just why don't we feel free to send us an email or post a question on the forum. If you have it, again, the information, most of this information is all available, and these examples are available from our website for download and for testing for your basically learning and evaluation. So again, I appreciate your time and look forward to having conversations with you in the future. Goodbye.